I'll present this work. It's ongoing work with Sanjoy Dasgupta at the UCSD. And it's going to be, again, on nearest neighbor type stuff, which is good because we talked so much about nearest neighbor so far. And so the goal is this, the high-level goal. So the high-level goal is on mode estimation. You get, suppose you get all these points, a lot of points. You have a whole sample from a distribution, an unknown distribution. And the goal is you want to estimate all the modes of the unknown distribution, right? So it's a very simple goal. It's a very basic problem. And the key thing we want to concentrate on here, the practical side, and the algorithmic side. We want to be able to come up with an algorithm that estimates all the modes of the density F at once, and also on optimality. So the problem is a very basic problem. You have a sample of size n from an unknown density, and you assume that this density has multiple modes, and you want to be able to estimate all the modes of the density. So we will have both an algorithmic side to the problem. How do you estimate these modes? What is the practical procedure to do so? And then there is also the estimation side, and we want to get optimal rate for doing so. Most of the time, most work on the subject have sort of concentrated on the statistical side. So, and usually they consider the single mode case, a density that has just one mode. And the point is to understand the rate at which you can estimate this density. So that's the case most considered. There is a lot of literature on this, and one of the works that established the minimax rates in terms of smoothness conditions is work by Sasha Tibakov. I cannot cite everybody, so the dot means and so much more great work out there. So the practical side. So however, the practical side has not received much theoretical attention and there are practical algorithms to do so. Many algorithms used, for instance, in vision. So the algorithm that's most used in vision for estimating the mode of an unknown density is mean shift. And you can view mean shift as doing some sort of gradient ascent on a smooth estimate of the density. And however, mean shift, although very practical, is hard to analyze. One thing is that it comes in many different flavors. There are many different versions of mean shift. There is some analysis, but the rates of convergence, finite sample rates are hard to establish. Some of the recent analysis is by groups in ACMU, Genovesi and Wasserman. Some analysis on consistency of certain versions of mean shift by Arias Castro here. And what we would like is an algorithm that is not only practical, so it's a real algorithm that can be implemented, but that also can attain the optimal statistical rate, right? And so that's sort of what feels to be missing in the literature. So we'll be deriving a rate optimal estimator, and it's going to be based on nearest neighbor graphs. And the great thing here is that I don't have to introduce nearest neighbor graphs anymore. We have had a good, we sort of getting a good understanding of nearest neighbor graphs now. And why am I choosing nearest neighbor graphs? Essentially because of what Ule said earlier. They encode the underlying density. They encode a lot of properties of the underlying density. And so it feels like a good way to start, taking a nearest neighbor graph and try to use the nearest neighbor graph to estimate in a practical way all the modes of the density of the underlying density. So this is, we're going to follow a simple program to derive eventually the algorithm. And we'll start off by just trying to understand nearest neighbor density estimation. Just a nearest neighbor density estimate at a single point. What are the rates we can get for just a nearest neighbor density estimate? And nearest neighbor density estimation has been studied for quite a while. And there are some asymptotic rates of the form 1 over square root k. by Bio de Vroy et al. Recently. And there is also some old work on the consistency of nearest neighbor density estimate. What we'll want here is high probability finite sample rate. We want to establish rate at a point for nearest neighbor density estimation, but rates that hold in a finite sample setting and hold with high probability. Then we'll try to gain intuition as to the simpler version of the problem, estimating a single mode. So we assume here the density has a single mode, and we want to estimate this mode. The common estimators in theory, this type of estimator, you essentially, they are plug-in type estimators. You essentially estimate the underlying density, and you're trying to find the mode of the estimate rather than the mode of the density itself. This is nice in the sense that it gives us a sense of the statistical problem, of the hardness of the statistical problem. However, it's hard to implement because this estimator might actually have multiple modes, right? And so it's hard to optimize this over the entire space. So rather, we'll look at a different type of estimator, which only looks at the argmax of a plugin over the data, over the finite sample that we have, rather than over the entire space. We do know that this one is optimal, and the question here is this one also optimal, right? And there is some consistency result from 2004 that shows that this one is consistent. It's a consistent estimator of the underlying mode. But what we'll want to show is that it's also a minimax-optimal estimator of the underlying mode. And the f hat that we'll use here is a k nearest neighbor density estimate. Then we'll get to the multiple mode case. Again, there are the practical procedures like min-shift, which are hard to analyze. And we want a procedure that estimates all the mode but just the mode, right? That has pruning also inside it. So that's essentially the outline. Throughout the talk, I'll just try to give a high-level intuition as to the ideas behind the analysis. And any more technical details we can take offline if you like. So KNN density estimation. Here, unlike what Ule was talking about earlier, we do know the distances, right? We do know the distances between nearest neighbors, between points. So RK here, RK of X, so imagine in a K nearest neighbor density, you fix a K, the number of neighbors you're going to look at. You fix the K. And RK here is going to be, RK of X is going to be the distance from X to its kth nearest neighbor in the sample. And that's the most important quantity here, that distance to the kth nearest neighbor. And the k nearest neighbor estimate is very simple. It just take k over n and divide by the volume of the ball containing the k points, right? And that's the estimate. And so VD here throughout will be just the volume of the unit ball in a Euclidean RD space, in a Euclidean space of dimension D. So throughout also we assume that X comes from some Euclidean space. So what's known earlier in 1977, De Vroy and Wagner established the strong consistency of this estimate. Earlier, there was this sort of square root k consistency rate established by Moore and Yackel. And so it just essentially says that fk of x converges to f of x at a rate of about f of x divided by square root k. And essentially this whole quantity converges to a normal, to a Gaussian, provided some smoothness condition on f and that k satisfies these conditions.
Are you sure about absolute value?
Sorry?
So I mean, you have an absolute value of the difference, and this converts to the normal distribution. So
but it's positive variables.
Oh, sorry, yeah. So, yeah. Okay, fk of x minus f of x converges to n01. But, yeah, I sort of care about the absolute value throughout the talk, and maybe that's why I left the absolute value there. So, so there are similar results by Bio and Chazal and Devroy in 2011, and under slightly different notions of smoothness. So again, we are going to seek high probability rate on the absolute value, rather than rather than on whether fk minus f is tends to a normal distribution, right? So we'll express the rate in terms of essentially the modulus of continuity of f at x. Essentially in terms of, because I'm not going to define it in terms of the modulus of continuity, but rather its inverse. So we'll define this simple r hat. And r hat here is essentially r hat, so you fix on epsilon, and you look at it, and we're going to throughout fix on epsilon, fix a point x. You fix on epsilon, and you're just looking at how far you have to go before f becomes epsilon bigger than f of x. Like how far do you have to go from x before f becomes epsilon bigger than f of x? And then we look at the other side also. How far do I have to go before f becomes epsilon smaller? And the question is, why not just define r epsilon of x? So how far do I have to go before it's either upper or lower? But it's important here to look at both differently, because at different points that we are going to consider, so especially at the mode, these two will be different, will behave differently. So we want to decouple them. And so essentially at the mode, r hat is infinity, while r check is will be a constant. So the first result is this one. The first result is this one. Essentially, with high probability over the whole support, so we consider every x in the whole support, and with high probability, simultaneously over the whole support, we have this sort of result, provided this condition on k over n, right? And the result, again, is a high probability result, and it gives us sort of a 1 over square root k, k rate. But now, in terms of this r, really, you have the two side, and you have the r hat and r check for either side, again. So it's a very simple rate, and you can convert it. You can convert this rate into rates in terms of smoothness at a point x, just in terms of the local smoothness of f at a point x. So if we assume that f is Lipschitz in this sense at a point x, or Holder in this sense, then we recover by just plugging in the right values for r. We recover this sort of rates at the point x, which are optimal in terms of the alpha, the smoothness parameter alpha. One aspect of this is that because we're looking at every point, and we're going to need to look at every point separately, because for mode estimation, we might have at the mode a higher degree of smoothness than away from the mode. Essentially, at the mode, we're going to require second order smoothness, while away from the mode, we don't need to. And we want to also understand how local can our assumptions be throughout, right? So the talk is not going to be very long, because I'm going to really just give out some of the high-level ideas. So the proof idea is the following. Rather than usually the way you'll proceed in general is try to decompose the problem into bias and variance, try to bound the bias and variance separately. However, we'll just go directly here. We'll go somewhat directly, and the bias variance decomposition will be implicit to the proof. So this is fk, and the main quantity that we need to care about is this rk of x. And so essentially, we do something simple. We just want to try to express this rk of x in terms of f of x, right? So imagine that you have some r, some radius r, for which is less than this r epsilon x that we defined earlier. Then you can imagine that the mass of a ball centered at x of radius r will be approximately f of x times r to the d, right? Because f is almost constant by definition. F is up to epsilon constant on this ball. And so the mass of the ball will be about f of x times r to the d. There is probably a vd missing here, the volume of the unit ball. And my squiggles just mean up to a constant, right? So now let's impose another condition on r. Suppose also that we pick the same r such that such that the mass of the ball is approximately k over n, right? Such that the mass of the ball is approximately k over n. Then plugging this back in, we can express this r in terms of f of x and k over n, just by plugging it back in, right? So again, very simple. Now, with high probability, it turns out that the empirical mass of any such ball will be close to its true mass up to about 1 over n. 1 over n rather than 1 over square root n. The reason why is because we're only considering balls of very small mass, about k over n. So if you use Bernstein types inequality, the balls of small mass would converge at a rate of about 1 over n rather than a 1 over square root n. So that's just another simple key thing, realizing that the sort of balls we need to consider are of the right, are in this regime, this small ball regime. So that's essentially it. And so if this happens, if this is true, then for such an r, rk of x must be very close to such an r. And that then allows us to express rk of x in terms of f. And plug that back in, and you essentially have the rate. However, we are assuming the existence of such an r that satisfies these conditions. So the proof is really just showing that such an r exists. And you are done. In the end, it's a very simple short proof, and which was surprising to us because we were surprised at first not to be able to find finite sample rates for this simple density estimator out there, and that the proof was so simple just by not having to try to go through a standard bias variance decomposition and going straight for the rate. Any questions? So that's the first part. And single mode rates. Now let's try to understand how we can get rates for just a single mode, assuming that f has a single mode, right? Now that I'm thinking about it, I feel like I probably wrote the talk very short because it was a 30-minute talk. I wasn't sure. I tried to be more conservative. So now for single mode rates, this is what we have. Again, like I told you earlier, what's most studied is this arc soup over the entire space of some Fn. And usually the Fn is a kernel density estimator. And why? Because it makes it sort of simpler. It's a kernel density estimator. If the kernel is smooth enough, you have a smooth estimator, and you can then talk about how to get the mode of this smooth function, right? Here we have a nearest neighbor. We have KNN, it's very unsmooth, and we have to think about it in a different way, how to get finite sample, how to get optimal rates for this estimator without having to appeal to the smoothness of the estimate itself. So there is tons of work on this. There are early work by Luc Devroy, much work by Sasha Tibakov on what they call recursive estimates, which essentially look at one sample at a time and create this sequence of estimators that are shown to be optimal for Holder classes. And then there are what are called direct estimates. And direct estimates try to do the estimation without direct estimate as opposed to plug-in estimate. They just try to do the estimation without first estimating a function. And in some sense, even though I'm looking at the argmass of fk here, it's still a direct estimate because we don't need to actually explicitly compute fk if we have rk being the distance to the nearest neighbor. We can really just take the minimizer of rk directly in the sample. So it's a direct estimate. There is no rate for such a direct estimate. And we'll try to give a rate under fairly simple assumptions. And we want the assumptions to be mostly local to the mode, not having it. So sort of intuitively, it feels that the rate at which you can converge to the mode should not depend on global assumptions about the density. It should depend on assumption locally at the mode. And so first, our main local assumptions are the following. Simply, by nabla square, I just mean the Hessian. Simply that the Hessian is negative definite, is strictly negative definite at the mode. And also, there is also one more assumption that f is differentiable in a neighborhood of the mode. So that's really just the assumptions, the local assumptions. And it's not a series of A1, A2 through A10 assumptions. It's really just this assumption, right? There is an A2 assumption, which is a global assumption. But it's a very simple assumption. We're saying that if I consider the level set of the density, each have a single connected component. And just a simple structural assumption that will hold if f is assumed to be, for instance, uniformly continuous. So very simple assumption is just the level sets are all contained within each other and a single one. So we then have the following result. Pick x tilde, which is the argmax over your random sample. Then with high probability, we recover the location of the mode up to this rate, k minus 1/4, provided k is between log n and n 4 over 4 plus d. Right. And this rate is optimal as the lower bounds were shown in the paper by Sasha Tibakov. And the constant here in the squiggle just depends on f of x and also on the Hessian, essentially on the eigenvalues of the Hessian at x. All right, so it's a very simple rate. And to us, it was very interesting that just looking at the sample, you can get the minimax optimal rate without having to optimize over the entire space.
Sorry, the dimension is also somewhere in the constant, or?
Yeah, dimension also appears in the constant, but dimension appears in the volume of the unit ball.
So it's minimax over this entire class of densities?
Yeah, it's minimax over density such that over this assumption here.
And so it's for which choice of k, the largest one you can take?
So okay, it's minimax over the largest choice here. Yeah. So I didn't say that. You have k minus 1/4. If you plug in the largest choice, you have n minus 1 over 4 plus d. That's what's minimal. That's what's minimax up to a second order smoothness assumptions. The main thing here is that the assumption here. We make it just locally, rather than in most of the results we found, we saw that they had to impose a lot more structural assumptions globally over the density. And so that was one of the things for us. And it's important for us also to just be able to get the assumptions locally for the purpose of estimating all modes eventually, right? So that's that part. So the proof idea. The proof idea is essentially the key thing. The key thing in the proof is to first notice that if you consider the distance from x to the sample, the distance from x to the sample with high probability will be within the right order. The distance from a point to the sample will be of the right order, and then the assumptions on the Hessian that we make allow us essentially to bound f locally at the mode by a quadratic. And so that means that f decreases fast enough, but not too fast. And so we can then say that outside a certain region, f is very small compared to f in very close to the mode. And in essence, there is a point that falls in here. As long as we can show that fk is much higher here than outside of here, we are good. Right? And to be able to have the assumptions being local, the original theorem 1 helps us here, because we can then only we can then have a different rate of convergence at the mode for fk and a different rate of convergence outside of it, and so that allows for a local result here. So so that's the intuition at essentially for a single mode. Now for multiple modes, we have again the same sort of assumptions now at every mode, and the algorithm is as follows. Suppose this were the density where you want to estimate all the modes. Then you start off this way. You start by considering the level set of this density from top to bottom. So this is the algorithmic part. Consider the level set of this density from top to bottom. Of course, we don't have the real density, but assume that for a second. And so as you consider the level set, let's say this is the first level set. It has a single connected component. We pick the argmax in all the points in that connected component. As you keep going down, more connected components appear, and whatever connected component you haven't visited yet, you pick the mode in that component, and you keep doing so. And eventually you recover all the modes. Right? And the same sort of analysis, we have to then localize it to these connected components. The next thing is, how do you really identify these connected components? And that just comes out of the fact that a nearest neighbor graph encodes all the connected components of an underlying density. And so, and there are some results on that in work, collaborative work with enriched. And so we just plug in that sort of result to recover the connected component and then run this sort of algorithm. The next thing is, how do you identify the false mode? So what I mean by false mode, the FK that you have is going to be jiggly. So how do you remove those things? Essentially, as long as you get a small bump, let's say you have little bumps here, as long as the bumps is of size less than the error rates that we have, you can suspect that it's a false bump, and you reject that. And you do this sort of thing, and in the end you can get, you can identify mode at the same optimal rate. We need to make an assumption on the mode, because essentially you have to sort of, when you are in a multiple mode situation, you need to have a notion of saliency of a mode. How salient is the mode? How visible is the mode? And so the notion of saliency we use is very simple. We will just say a mode is R salient if, in order to get from this mode to another mode, I need to jump over a valley that is about R big. Okay, so it can be defined properly, but intuitively that's what we mean. And you fix an R salient mode, we can then recover an R salient mode at this optimal rate. And this will hold then for all modes of the density with this simple algorithm. And we have also another result on pruning these modes, that the modes that you recover, all the modes that you recover correspond to true modes of the underlying density. And at a rate of about log n over k. So that's essentially it. This is just some simple, do I still have a minute? Essentially, yeah. So this is some simple simulation. And in the simulation, all we do here is we compare this algorithm on different types of nearest neighbor graphs. This here is just a normal nearest neighbor graph where you connect every point to its k nearest neighbors. And this one is another type of graph where you connect a point to another point only if they are both nearest neighbors of each other. And this one is more brittle, and it's harder to recover the modes with this one. But with this, and here the experiment is just over a simple mixture of 5 Gaussians, but quickly with the nearest neighbor graph we recover the mode locations. And so that's it. That's essentially it. Thank you.
So I assume that in practice you need to somehow choose k. Do you have some close validation method to do it? Or?
So the results hold for any k essentially greater than order log n. And yeah, in practice you...
If you actual data in the kind of the... What? Actual data?
So yeah, so in practice, yeah, I don't know how you choose K properly to get the optimal rate itself, right? So yeah, in practice, I don't know how you'll do that. So what we did here is we chose K by cross-validation over, yeah, over the sample, that's it.
What is the criterion used for it?
Sorry?
What is the criterion used for it? Not for the density itself?
Yeah. The log likelihood, we just optimize the log likelihood and choose K that way. But it's not clear that's the right way. So in practice for unsupervised problems, it's fairly generally unclear how you properly choose K. But there is some recent work by Ingo Steinwartz where that I still have to read properly. Where, but it's not for nearest neighbors. It's for density estimation with it's for kernel density estimation, where he chooses the bandwidth automatically for identified level set of a density. But it might be a good paper to look at also. Yeah.